Hey kids, this is Mrs. Mooney, and this is a video about inverses of functions. And here's a joke for you about the stuff we just did, so, hopefully you get it now, right? Alright, so let's start with the only rule of inverses. To find the inverse of a relation, switch x and y. And I said relation because it could be a function, it doesn't have to be a function, but to find the inverse, switch x and y. It is that easy. So here we go. We're going to start with an example. Easy. Original relation. Hide that answer there for a second. Alright, we're going to plot these points. Alright, we have the set of these points. 2, 1, there, and 3, 3, there, negative 4, 2, so there, and 4, negative 3, there. Alright, nice and boring, right? And all I said was to find the inverse, you just switch x and y. So I take 2, 1 and turn it into 1, 2. That's there. And I take 3, 3. Well, I switch it, I still get 3, 3. Negative 4, 2 becomes 2, negative 4 down here. And 4, negative 3 is now negative 3, 4 up here. And if you look at it, we kind of have a reflection. And what it truly is a reflection over this line. Right here, the line y equals x. Each point is reflected directly across there, see? And if it's on it, then it stays on it. There's a smaller version. Alright, so now to find the inverse of a function. It can be a relation or a function. Use same rules. You switch x and y. So here's another example. It says original function f of x equals 2x plus 1. So we're going to find the inverse of this function. That means we're going to switch x and y. And remember, this is like having a y. So I'm going to have x equals 2y plus 1. We just switch x and y. That's all we have to do. Now, I can't graph it as an x equals, so I need to rearrange it and solve for y. That means I need to take away 1 first, and then divide everything by 2. So I have y equals, and then I can split these up. That would be 1/2 x minus, and then that would be 1/2. And if you put it as x minus 1 all over 2, that's fine as well. You're just used to graphing lines in points or in slope-intercept form, so you might want to divide both by 2 so that you can know that the slope is 1/2 and the y-intercept is negative 1/2. And if I graphed each of these, I've put the original in red. 2x plus 1 has a y-intercept of 1 and a slope of 2. And 2y plus 1, x equals 2y plus 1, remember we rearranged it. And so it has a y-intercept of negative 1/2 and a slope of 1/2. 1 over 2, just like that. So it's right here. Notice that it is also reflected across the line y equals x. Your inverses will always be reflected across the line y equals x. And another question you want to ask yourself, is the inverse of this function also a function? Remember, to be a function, each input has to have only one output. Or in other words, each x has to have only one y. So is it? Yes, a line is always a function. And if your inverse is also a function, you can write it like this. The little negative 1 power just means inverse. So if I said, if I just gave you a function, g of x, and said, what is g to the negative 1 of x, you now know that I would be asking you for the inverse. Alright, now, another thing I would ask you to do, and I don't think this is in your book, but we're going to be doing this anyway, verify if two functions are inverses of each other. And to do that, you're going to take f of g of x, which just means I'm going to plug this function into that function, and g of f of x, which means I'm going to plug the f function back into the g function. And if I simplify both of those, they will both equal x. So let me show you what that looks like. Here's an example problem. I want you to verify for me that f of x equals 1/2 x plus 2 and g of x equals 2x minus 4 are inverses. And when you just look at those two functions, those two lines, you're like, I don't know if they're inverses or not. They have different slopes, they have different y-intercepts. So what you're going to do is you're going to, if I say verify, I need you to do this. I don't want you to find the inverse and then show me, yeah, that's right. I want you to take f of g of x. So this will be our f of x, and this will be our g of x. Means we're going to take 2x minus 4 and put it in place of this x. Okay, so I'm going to have 1/2, and then instead of x, I'm going to have 2x minus 4, and then I still have my plus 2. So half of 2x would be x. 1/2 of minus 4 would be minus 2, and then I have a plus 2 out here. And x minus 2 plus 2 equals x. So that equals x. However, you have to do both. So now I have to take the f of x function and put it into the g of x function in place of x. So now I need 2 times, and then instead of x, I want 1/2 x plus 2. I want the whole other function, and then minus 4. So now I can simplify this. 2 times half of x is x. 2 times plus 2 is plus 4. Minus 4. X plus 4 minus 4 equals x. Therefore, they both equaled x, and we have verified it. You've shown me on the paper that they both equal x with check marks. They are inverses of each other. Another thing I want to mention to you guys, the term one-to-one. If a relation is one-to-one, that just means each one x has one y, or many-to-one. So I could have many x's with the same y value. That means like this has this y value, and this has the same y value, and this has the same y value. If it's one-to-one or many-to-one, then it's a function, right? Every input has one output. But if it's one-to-many, so if my one x value has many different y values, then it's not a function. So one-to-one and many-to-one and one-to-many are some terms you might think about when you're talking about defining if something is a function or not. An example of this would be the function y equals x squared, or f of x equals x squared. That is a many-to-one function. We have many x values, and each of those x values has one y value associated with it. So that is a function. However, if I took the inverse of a parabola, I would get a parabola, but it's laying on its side. That is now one-to-many, because this x value has 1, 2 y's, and this x value has 1, 2 y's. It's one-to-many. And if it's one-to-many, it's not a function. So if I were to be working with quadratics and I had f of x equals x squared, and then I switched my x and y, so I had x equals y squared, and to get y by itself you have to take the square root, and don't forget your plus or minus. The plus gives you the top part of it, and the minus gives you the bottom part of it. That's not a function, so you cannot say the inverse is plus or minus the square root of x, because that's not a function. It's a relation, but it's not a function. Now, there are some ways to work around that. If I took the domain of f of x equals x squared and I restricted it to only non-negative real numbers, non-negative, remember that's positive and 0, then the inverse would be a function. So let's do an example of one of these. If I had y equals x squared plus 2, that's a parabola, a vertical parabola, but I'm restricting my domain to x has to be greater than or equal to 0, so only positives and 0. When I graph this in the calculator, there's a trick. You can graph it on, by hand, easy, right? But only the x's that are greater than or equal to 0. So starting with 0, we'd have 0 squared plus 2, and then 1 squared plus 2 would be 3, and 2 squared plus 2 would be 4 plus 2 would be 6, and so on. But we only graph that half of it, because we're only graphing from 0 on out. And you can put this in your calculator. It's kind of neat. You're going to go to y equals, and in y1, you put your function in parentheses, and then you put a slash, a divided by, and then in another parenthesis, you put your parameter. And we can find that greater than or equal symbol right there. If you go second math test, there's all the inequality symbols in there. So you could actually put it in your calculator if you entered in just like this, and it will look just like the graph we just graphed with only half of the parabola. So now here, to find our inverse, Once again, the only rule is switch x and y, so I've got x equals y squared plus 2. We take away 2, and then we take the plus or minus the square root. However, we had a restriction on our domain, and when you switch x and y, that now goes to the restriction on y. And so if y has to be greater than or equal to 0, then this plus or minus thing goes away because we can't have negatives. Negatives are not greater than or equal to 0. So our inverse is just the positive of the square root of x minus 2. And so when you graph that, we originally had this parabola up here. Now you're going to have, look at this, shifted to the right 2 units, and it's only the positive part of that parabola that so they're reflected over the line y equals x. They're inverses of each other. Those would both be functions because we've restricted our domain. Another cool thing you can do with the calculator, and this is just an extra little trick you can use for yourself, is you can put the original function in y1, and then you go to your home screen, and you can hit Second, Program. Just try this at home. You don't have to memorize these or anything. This is just for you to kind of see how to do it on the calculator. And then you can choose number 8, go to vars, y vars, number 1, y1, and enter. Just go through all those steps, and you can actually graph the inverse. And so even if you didn't know what the function was supposed to be, you could still get your calculator to do it. And then you would see which one is which. Then you could also graph what you thought the inverse was and put them on top of each other, and it should be exactly the same. And of course, to graph by hand, which I'm going to be asking you to graph things by hand, but all you would have to do, even if it was the most crazy function in the world, is to make a table of the original, right, and plot points for the original, and then switch your x's and y's, and then plot those points, and then you would have a graph of your original and your inverse. Very fast, very easy. Alright, that's the end of that video. I know it's not Monday, but whatever, here's a joke for you. Y'all have a good night.